then we work with some guys in France, and we forget about it, and working with people in Russia, forget about it. Then I had a PhD student in Sweden, and it's on and off. But there are interesting things coming up. The thing with this kind of models is that it has connections with many areas of probability and mathematics. And I'm still very unhappy because I haven't found all the connections, and I'm not an expert in everything. So I'm desperately looking for people, for example, who know random matrices and stuff like that, because they pop up in these kind of things. Okay, so what I'm going to give you is I present is sort of overall picture of this edifice. And contrary to what Kostya suggested to me, I am not going to explain anything except bits and pieces, okay? Because if I start explaining something, I may end up wasting half an hour of your time. So I hope, however, to give you some ideas. Okay, so let me put let me say what this talk is about. So everybody knows Erdos-Renyi graph. The directed version of Erdos-Renyi graph we now call Barak-Erdos graph. We didn't call it so when we started working on this. And when I say we, I mean me and many co-authors, like you can see here, from Russia, from France, from Sweden, and so on. Okay, I will not give references. I will not pay tribute to too many people because I don't have the time. I'd be happy to give you papers and references afterwards. Okay, so the directed version is called Barak-Erdos graph because Erdos with, I think he was a computer scientist in Israel called Barak, wrote a paper on the directed version of the Barak-Erdos graph. So you take you just give directions to the edges of the Erdos-Renyi graph. Now, you add to that things like the structure of the vertex set. It could be it could have a natural deterministic order, a natural deterministic metric, for example, and then you put random edges on top of that. You can put weights on the edges and all these kinds of things, and you can make the probabilities themselves, the probability P of the Erdos-Renyi graph, depend on the structure of the vertex set. So, many possibilities exist. We have to start from somewhere. The point is that we're always interested in longest paths. So sort of like last passage percolation problems. We have a vertex I, a vertex j, and we want to compute or to say things about what is the longest path that takes you from I to j. If we have no weights, then we measure the length of the path by the number of edges in the path. If we put weights, then we talk about the length of the path without weights and the weight of the path, which is the sum of weights. And mind you, I am going to add sometimes negative weights as well. So why would you add weights? If you think of getting a reward, for example, going from I to j, you want to maximize your reward. What does negative weight mean? It means that you might have to pay something. Why would you have to pay? Because paying a little bit might take you to a vertex from which there is a higher reward. Okay, so it makes sense to add negative rewards if we also take the point of view of combinatorial optimization. And yes, these things appear indirectly in combinatorial optimization problems. I will mention at least one indirectly. Okay, so now let me put the applied hat. So there's a lot of interest in mathematics probability. In particular, we get interesting limits that are related to random matrices. So that enough, I think, generates interest in mathematics. There are models in statistical physics related to these things. These random graphs appear in connection to parallel processing systems in computer science. And this is an old problem in performance evaluation where you have, let's say, programs coming to a parallel computer, and they have tasks and subtasks, and this cannot be executed in parallel, but there is a certain structure between them. So you cannot start job A before job B finishes, and so on. So you have a certain structure. And if this come according to a certain rate, and the processor processes the jobs according to certain rates, then we may ask, what is the stability condition of these things? What is a condition that will keep the system stochastically bounded? And that depends on the longest path of or heaviest path in your task graph. Then there are models in mathematical biology, especially in ecology. There is even a book written on these things where longest path describes a food chain. Okay, so the survivability of a species on an isolated island depends on the longest food chain. And also in computer science, and this is where the name Barak Erdos first appeared. It was a paper by Jansson, Bolobas, and Brightwell. They were looking at linear extensions of a partial order. Okay. So here is what the Barak Erdos graph is. On the vertex set Z, I take the integers, infinite set, and for I smaller than j, take two integers, I smaller than j, and put the edge ij with probability p, or not with probability 1 minus p. Okay, so this is an infinite graph with infinitely many edges, and it looks like that. I mean, it is not possible to draw it really, because unfortunately, you know, I feel I don't work in areas where you can produce nice pictures. I really admire people that they can put these nice fractals and stuff like that, but I have nothing to put usually. So even this picture is stolen from the internet, and it is the Bible here. This is the Bible, that's Genesis, and this is the Apocalypse. And it says, it puts an edge between 2 points that are referenced. I mean, because it's the Bible, you can reference the future, or you can refer to the past, and so on. By the way, there's a similar graph between points that, points where you have contradictions. I don't make a theological statement or anything like that, but I found that this is an interesting way to see a sample path of this graph. It remains to statistically analyze this and see how it fits. I don't know. Okay, so I'm lazy, I didn't draw anything. What happens here is that if we take the maximum length of all paths from vertex 0 to vertex n, then we can easily see that ln divided by n converges almost surely to a constant that depends on p, almost surely in L1. Why? Because we have subadditivity. If I take two vertices at distance n and two vertices at distance m, so 0, n, and then n plus m. Can you see me because I'm waving my hands? I don't know if you can see me.
Yes, we can.
Okay, so I'm used to be giving talks where I do a lot of hand waving and a lot of writing on the board, and so that's okay. So n, m, ln plus m, okay, the longest path from 0 to n plus m is at most ln over here, plus something that is distribution to lm, plus 1, because there might be an edge that connects between the two islands. So that's subadditive. And by Kingman's subadditive ergodic theorem, we have for free that ln over n converges to a constant, and that constant is given as the infimum of expectation of ln divided by n by subadditivity to deterministic sequences. And therefore, in fact, this works even if we have a stationary and ergodic framework, which means that we, for this kind of limit, we don't care about independence as long as we have a structure that is translation invariant and ergodic. Okay, so we get that for free. But the problem is always is, what is this constant? How does this behave as a function of p? We know that it is an increasing function of p. It's not difficult to show that it's continuous, but what else? So by the 90s, early 90s, it was known by papers of Newman what the behavior of C is when P is very small, so a sparse kind of graph. So there was a Taylor expansion of order 1 there at P equals 1. So here I'm giving you this, a graph, as a function of 1 minus P. So this is 1, so it's decreasing. And here are 2 bounds. So the actual curve is between the lower bound and the upper bound. And these are really complicated functions, even though they look like straight lines. They're not straight lines. And see, and this, it's not, they're not convex even. So we have, by, let's say, 15 years ago with Sergei Foss, we had very good bounds in this region and not so good bounds in this region because the upper and lower bound do not match derivatives even. And the way we obtained that, I will give you the model that we came up with, included 2 elements. One was extended renovation theory, which is due to Alexander Borovkov, which is the generalization of the Harris theory in the context of stationary and ergodic recursions, and the construction of a particle system that at the time we called infinite bin model, which is an unfortunate name for 2 reasons, because it spells IBM. And then later I worked on something that I called infinitely iterated Brownian motion that I again called IBM. That's unfortunate, but I have nothing to do with IBM. Okay, one thing that we should keep in mind is that when we talk about maximal length between 1 and n, we may either mean from overall paths from 1 to n or overall paths between 1 and n. The 2 things are asymptotically the same because we can prove that almost surely any 2 points will be connected as long as the 2 points are far apart. Okay, so there's always a path. As long as the probability P remains constant, bounded away from 0, the 2 far away vertices will always be connected. Okay, I'll say more about that. So what is the infinite bin model? That's the first idea, and I wouldn't come back to that unless our French partners exploited that further and were able to obtain a full asymptotic expansion of the whole function and prove that this function is analytic and many other things. And I'm going to give you that formula. But first, let me describe the ideas here is grow the graph little by little, start with 1 point, let's say point 0. And then let's take point 1. Toss a coin, we connect to 0. All right. So give 0 weight 0. Give 1 weight 1 because there is a path of length 1 between 0 and 1. Now go to 2. Okay. So try to connect to 0, failure. Try to connect to 1, success in this picture. So give it weight 2 because there is a path of length 2. Now go to the 3rd vertex. The 3rd vertex only connects to 0, so give it weight 1. Go to the next one, it's not connected, give it weight 0. Go to this one, and this one is connected to this and to this. So the maximum path is again 2. So what I'm doing here is I'm adding a new vertex each time, and I look at the maximum path backwards. All right, and I call that weight of this vertex. Now, when I'm performing this experiment and I'm interested in the maximum weight, I can start the Bernoulli trials from any previous vertex I like. So I may as well start with a vertex that has maximum weight. If I connect to a vertex with maximum weight, I don't need to continue my experiment because my weight is going to increase by 1. If I don't, then I go to the smaller weight, maximum weight minus 1. Do I connect? If yes, then I again have the maximum weight. The maximum weight does not increase. All right, so we can describe it by bins. So let's put a bin here to the right by putting the number of vertices with maximal weight. Forget the top part. The top part corresponds to the new one. So far, the maximum weight was 3, so I put two particles here. This is the bin labeled 3. Now go to the bin labeled 2. Again, I have two particles. Go to the bin labeled 1. Again, two particles. Go to the bin labeled 0. Again, two particles. Okay. So I have this particle system where I keep track of the types rather than the actual labels of the vertices. Okay. So if this particle appears here, this vertex, I want to connect. I will try with this one, the maximum. If this is a failure, I will try with the next maximal one. If this is a failure, then I will try with a vertex from the previous bin. Let's say I have success. Okay, so the maximum weight remains the same, but I now have a new ball, a new particle at the bin that corresponds to the maximal weight. Okay, if I connect to the maximal weight, that's the alternative here, then I just put a new bin with one ball because the weight has been increased. So we call that the infinite bin model. This is a particle system that has appeared in various guises before. This turned, not this exact one, variants of this. So it turns out that if we look at the contents of these bins, enumerated in a way so that this bin is called 0, this bin is called -1, -2, and so on. So this becomes a Markov process that has a unique stationary version. And we have convergence to this stationary version in total variation of projections. We cannot have convergence in total variation of the whole Markov process because it's like a snake that lives in sequences of finite length, and at infinity, it jumps to sequences of infinite length. So it's not possible to have convergence in total variation when before the limit you live on one set and at the limit you live at a disjoint set. You have convergence in weak convergence, but when you restrict this to the first, let's say, 5 bins, then you have convergence in total variation. Okay, so what happens here by exploiting this Markov process? Exploiting this Markov process, we have a well-defined recursion now, and we can write balance equations. We can say, how do we relate n plus 1 to n, and write all sorts of recursions that cannot be solved, but which can lead to inequalities and various other nice things. And this gives us the upper and lower function that can be described analytically. Okay. Other things that we can get because we have this Markov process are central limit theorems. And there are two kinds of central limit theorems. The first one says, take the total contents of all bins up to NCT. C is the rate of growth. NCT is just a deterministic number, go up to the expected rate of growth, subtract the expectation, divide by square root of n. Okay, that converges to a Brownian motion. If instead you don't look at NCT, but look at LNT, so you look at something that is a fraction of the maximal length. Maximal length is the total number of bins we have. Then the Brownian motion gets tied down to be 0 at t equals 1, because at t equals 1, that becomes the total content of all bins, and it converges to Brownian bridge. Okay. So these are two functional limits. Now, let me tell you what Bassiamala and Sanjay Ramasamy did. They looked at IBM in the framework of IBM with the parameter mu, where mu replaces the geometric random variable that we were using. Why geometric random variable? Because, as I said, when you have a new vertex and you try to connect to one of the previous ones, you start with the vertices of the first bin, then the next bin, and the next bin, and you just have a geometric random variable to find out where the first success is. So you just select where you go according to a geometric random variable. If you generalize that and you say, I have a different distribution, then I have a generalized version of this infinite bin model. For example, if I take mu to be the uniform distribution, so uniformly overall over everything in the past, then we get something that I don't know what it's called, but it appeared in a paper by Aldous and Pittman in 1983, when they were trying to answer a question posed by a computer scientist at Stanford. At the time, he had done his PhD, and he had a combinatorial optimization problem that turned out to relate to something else that turned out to be described by this. So Aldous and Pittman studied this in the context of computer science / optimization. So if we let v mu be the speed of the front of this particle system, so this particle system is a snake that grows, okay, it cannot decrease, and it is the rate of growth basically. Then v at the geometric random variable, when mu is a geometric random variable with parameter b, becomes our constant c of p, and this is basically what Malai and Ramasamy obtained. This EP was known by Newman a long time ago. They added this correction, and this, in fact, they have a much bigger formula. You can find bigger and bigger and bigger terms. If you, and they did that by looking at the details of the evolution of the infinite being model, describing the states by words and using different methods to obtain that. They actually proved that this function is analytic. Okay, so let me go to the next thing that we can do. We can make the graph elastic, which means that we can make the probability depend on the natural distance between two vertices. So instead of having p, let's have pij, and this being a function of j minus I, okay? So, but do not make this going down to 0 as the argument goes to infinity, sufficiently fast, sufficiently slow, I should say, so that this series is finite. For example, if pi is a constant, it will be finite. If pi goes to 0 very fast, this will not be finite. And the reason for that was because we came up with the idea that there is a way to define, to obtain a regenerative structure in the graph. Okay, so let's define this skeleton points, we call them. Skeleton point is a vertex I that has the property that there is a path to any bigger vertex, and there is a path from many lower vertex. So this is connected to everything to the right and everything to the left. The first question is, do skeleton points exist? It's actually not very difficult to show with using geometric random variables and elementary arguments that they do exist. And in fact, they are they're frequent. I thought that they were very rare, but then at some point I decided to put a number in. I put p equals 1/2 and I computed the rate, and I found, oh, every 4 or 5 vertices will be a skeleton point. Wow, I thought it would be every 200 vertices when p equals 1/2, but that was wrong. Every fourth vertex is connected to everything. Oh, interesting. Connected by a path, not connected, of course, by a direct vertex. And the reason for this summation is because if you compute the rate of this random set, thought of as a point process, if you like, you find that is given by this infinite product, is 1 minus q1, let's say, q2, qj squared. Without the square, I have the probability that you connect to the right, and the probability connect to the left because of symmetry is the same, so we get a square here. That's the rate. If you put pi equal to 1/2, you get some very reasonable number. Okay, now the interesting thing is that these are not just random points that appear frequently with finite expectation between any 2 points, but they also form a renewal process. Okay, so the distances between successive points are independent, except the 2 points that contain 0 or contain a particular point, because of the usual thing that will have a different distribution, a bias distribution. So it's a renewal process, and not only that, but the whole graph regenerates over this, which therefore what this entails is that if we want to look at the maximum length between 0 and a very large vertex n, this maximum, the path that achieves the maximum, must pass through every skeleton point between these two vertices, because the skeleton points are connected to everything, so you are just losing if you don't go through them. And then what happens is that the maximum length becomes as sums of maximum lengths between chunks. So a maximum of a random variable becomes sum of IID random variables. What could be better? Sums of IID random variables, and therefore we can get everything by looking between successive skeleton points. So we can, of course, recover the central limit theorem. We can we can recover the low large numbers, the central limit theorem. We can get large deviations, whatever we like. Except there is one catch, that there is an unknown constant somewhere, the sigma squared, which relates to the variance of the stuff I have on a cycle. Okay, that is not something that we have tried to compute. We know it is finite. We have not tried to compute. That's an interesting but very tedious problem. We have been lazy and we have done nothing about the variance. Okay, so the next thing, I will tell you now how this connects to random matrices and Brownian percolation. So instead of the integers, let's take, forget it, look at this picture, but simplify it. Think of only the lower line and the upper line. So this is the integers and a copy of the integers. Okay. So we have two parallel lines, and let's do the following thing. We have a Barak Erdos graph on each line, except that from time to time introduce the possibility of going from the lower line to the upper line. So we have a probability P, let's say, of jumping from down to up, okay? And we're interested in the maximal path from the beginning up to some point. So the maximal path will go to the lower line for some time, and then it will go to the upper line and end up here. Now, this picture here is supposed to be generalization when you allow not just parallel copies of the integers, but also parallel copies that at each point of a finite partially ordered set with the least element and the greatest element. And this describes the functional central limit theorem, but perhaps it is easier to say what happens when I just have a 2-point set. All right, so consider just 2 points, just two lines, and let B0 be a Brownian motion associated to the lower line, and B1 a Brownian motion associated to the upper line. And define the process Z of t to be the maximum, when S ranges between 0 and t, of the increment of the lower Brownian motion between 0 and S, plus the increment of the upper Brownian motion between S and T. Okay, so this is a well-known process that appears in so-called Brownian last passage percolation, and it is known that if we consider a 2x2, in what I described here as a 2x2, m by m in general, a random matrix in the Gaussian unitary ensemble, then so these are random matrices, random unitary matrices with Gaussian entries of specific form. Then Z of t is self-similar like Brownian motion, obviously. Of course, it's not a Brownian motion, but its distribution at time t is square root t times lambda 2, in my particular case, where lambda 2 is the largest eigenvalue of a 2x2 such matrix, lambda m of an m by m matrix. Now, it is also known that, so this is a connection with random matrices. It's also known that if m goes to infinity, then, sorry, let me backtrack. I'm describing you a process, and I'm telling you what the distribution of this process is. The theorem here is that the functional central limit theorem associated to the maximal length of the graph with 2 lines will be this particular process. That's what I'm saying, which we understand. Now, if we take another limit as m goes to infinity, then we have that lambda m minus 2 square root of m times m to the 1/6 converges in distribution to the famous Tracy-Widom distribution that also appears in random matrices, describing the distance between the largest eigenvalue and the second largest eigenvalue. Okay, so I can obtain Tracy-Widom distribution by taking limits in series. First of all, doing a central limit theorem, finding something that depends on m, and then m goes to infinity. So the question I asked some time ago with a PhD student from Sweden was, can I obtain this limit directly? Well, what does it mean? It means that if I think of many parallel lines of the integers, then basically I have the integer lattice. Okay, so I have the integer lattice where I take two vertices of the integer lattice, one here and another, and another up. So compare them in component-wise partial order. You have one up, lower, one upper, and then toss a coin and go from one to the other with probability p, add an edge with probability p, or do not add an edge. So is it possible to say I start from 0 and I go to a vertex very far away from 0 and I get the Tracy-Widom distribution by some kind of central limit theorem? Well, yes, but we can only do it in the case where I take the faraway point to be the upper point of a rectangle that increases in a way that the horizontal side goes to infinity much faster than the vertical side. And this is an artifact of the proof rather than reality. And the proof for this is basically putting this, this structure here, embedding it in last passage percolation with Brownian motions by using the so-called Hungarian theorem Komlos major to Snadi. So the best possible coupling of, which is the generalization of coupling, embedding a random walk in a Brownian motion. So here we embed bigger structure in Brownian motions. And then we use the previous result from last passage percolation to obtain this. So we're cheating. Okay, and the reason we're cheating, of course, is obvious, because we obtain a result that is not optimal. We believe that this result remains true when even when a is equal to 1. Okay, so that is if this goes to infinity like a square. But I don't know how to do that. In fact, that's a very difficult problem because we know that the corresponding last passage percolation problem is very difficult. So there is this famous paper by Kurt Johansson several years ago, where he looks at last passage percolation problem, which means the following: take the integer lattice, and to each vertex of the integer lattice add a weight which is an exponential or geometric random variable, and make the weights IID. There are no weights on edges here, just on the vertices. And then take a path that is a non-decreasing path and measure its weight by adding the weights of the vertices. How does this behave? Okay, so there is this paper, which has a very different flavor from anything we're doing, because it uses explicit methods for proving the limit theorem, namely the Tracy-Widom distribution, by using various transformations, in particular the so-called RSK correspondence of that is known in computer science. So this is a hard problem. So it's a hard problem in a particular case. It's a hard problem in our case as well. Okay, so now the next thing I'm going to do is I'm going to consider a kind of light traffic regime, as we say in queuing theory. So we're going to make this probability P be very, very small. And what we're going to discover is an object that also was defined by Aldous, and Aldous and Steele have a review paper on that several years ago, that is called PWIT, meaning Poisson-weighted infinite tree. So I'll just describe this object first, and then I'll tell you how we obtain it. So I have a root and I have infinitely many children. Now, I I have now for each of these I generate a Poisson process. This distance of the first child is supposed to be the first point of the Poisson process. This is the second point. This distance is the second point, so it is bigger than this is the third point, the fourth point. Okay, so I have a Poisson process, and I put the children according to these lengths. Then for each of them, I do exactly the same thing. I have an independent Poisson process, and I put their children at the first point, the second point, the third point, the fourth point, and so on. So this is an infinitary tree, because in analogy to infinite binary tree, it's infinitary tree. And of course, you can see that it's self-similar. So if you have an object like this, you can do many things, because you can write a recursion. If you have a function of it, you can write the function of it to its children and write the recursion equations and things like that when you have such a self-similar graph, self-similar tree. When you have a graph like what we have in our case, it's impossible to write recursion. However, when P is very small, our graph looks like a Poisson-weighted infinite tree. Namely, and this is something that has also appeared in the physics literature, and physicists call it continuum cascade model. So let's consider the Barak and Erdos graph on, it's called GN, not on the integers, but on the integers where I make the distance between the two integers 1 over n. So I put 1 point at 1 over n, and let's take the probability to be like 1 over n. N times p converges to 0, the usual Poisson scaling. Then the graph GN converges to a Poisson-weighted infinite forest, because I'm only going to get a tree if I consider the connected component of 0. At some point, I may lose connection. Well, add a new independent Poisson-weighted infinite tree. So this converges to a Poisson-weighted infinite forest. The component of the graph that contains a particular point, for example, 0, converges to, sorry, this is a typo here. It's supposed to be Poisson-weighted infinite tree. And this is a rigorous theorem, meaning that it converges in the sense of convergence of probability measures in metric spaces. So, so if P is very small, the take-home message is that in this Poisson limiting regime, the Barak and Erdos graph looks like a random self-similar tree, and hence recursions are possible. One can write recursions and analyze these recursions and get some results. These recursions are sometimes integral differential equations, so they're not solvable, but at least you have something that you can play with. And this is what the physicists have done in quite independently, sort of appeared a model that was of interest in statistical physics. Other things that we can do, I'll go quickly over that. We can add weights to the vertices and to the edges, if we like. And even if when we do that, we can obtain regenerative structures, central limit theorems, and so on, provided that the vertices have sufficiently many moments. So if we add weights on the edges, the take-home message here is that in order to obtain a central limit theorem, these weights must have a second moment, finite second moment. If we want a law of large numbers, we must have finite second moment. If we want a central limit theorem, we must have a finite third moment. And that's because when we now try to define a regenerative structure, we also have to take into account the weights that will lead to something more complicated, and then the moment conditions come from analysis of this regenerative structure. Right, so, and now I come to the last part. How much time do I have, Nathan, or?
Probably like 10, 15 minutes.
Okay. So this is the latest work here, where we every time we do something, because we're not too smart, we realize that there is an additional structure to that thing, and we keep saying we're stupid, we didn't think of that before. So all this complicated notation is supposed to mean the following. I talked to you about skeleton points. Think of the Barak Erdos graph, okay? Forget about weights or anything like that. I said that there is a regenerative structure. Now, if I asked myself, can I take the regenerative structure in a way so that I can simulate my graph by simulating the independent chunks of the graph between two skeleton points? Actually, that was not obvious because we hadn't asked this question before, and we had to think. And we realized that yes, we can. And that's what this is supposed to describe, that we can actually construct the Barak Erdos graph by first constructing a random variable that takes values in the set of finite directed graphs, and this is what is described here, and then putting these things together, and then tossing extra coins to decide what the skeleton points are doing. Okay, so, and the reason we wanted to do that is because we wanted to study the constant C, not only as a function of P, but also as a function of the distribution of the weight. Now that's a complicated problem. How do you, even studying the function C as a function of P only is a hard problem. If we add weights, what does it mean even to study it as a function of the distribution of the weight? I mean, mathematically, it makes perfect sense, but in practice, what do you do? So we start very modestly and we say, let's take weight with two values, all right? So here are the integers, and I have a coin that has success with probability P, failure with probability 1 minus P. Take two vertices. If success, join them with the blue edge and put weight X. Sorry, put weight 1, put weight 1. If failure, then join them again, but put weight X. So the blue ones have weight 1, the red ones have weight X. If X is equal to minus infinity, as far as the maximum length is concerned, that means absence of this, and when I go back to the Barak Erdos graph. If X is bigger than minus infinity, including negative, then I have some other beast. If X is equal to 1, then I have nonsense because it's just the full graph. So blue edge, probability P has weight 1, red edge with probability 1 minus P has weight X, which could be negative. And sometimes it actually makes sense to have a negative edge because, as I said, I may have to pay in order to go to a point from the better point, the maximum weight to the right. So now here I obtain a constant C, that's a function of P and X. Okay, so what happens to this constant as a function of X? And there is an interesting thing that happens, and that's what I'm going to describe. First of all, let's let Wxij be the maximum weight of all paths from I to J. Call this graph GP of X, with GP minus infinity being the Barak Erdos graph. Now, again, we have that Wx0n divided by n, I have a central limit theorem, converges to a constant Cp of x, and this limit is true for all x, including minus infinity, where Cp of x is deterministic, and the limit of Cp of x as x goes to minus infinity is the previous function that I told you about, Cp. I put subscript p rather than parenthesis p here. Okay. And we're interested in the behavior of Cp of x as a function of x for fixed p. The first thing we see is that Cp of x is a convex function of x, and that's obvious because the weight of a path is an affine function of x, because what I'm doing is I'm adding ones and x's. So I have so many ones plus so many x's, an affine function of x. I take maximum of affine functions, which is a convex function. I take expectation, which is a convex function. So Cp of x is a convex function of x. So right and left derivatives exist everywhere. Do they exist everywhere? Is it smooth? By coupling, actually, we can find this interesting thing that Cp of x divided by x is C1 minus P of 0. You can get things like that by looking at coupling and self-similarity and things like that. So left and right derivatives exist at every x. Let's let d plus be the right derivative with respect to x, and d minus the left derivative. It is not difficult to see that if x is irrational, then the left and right derivatives are the same. But is it that do the derivatives exist, fail for other points? Okay, so here is the result. The set of x for which Cp of x fails to be differentiable is precisely the union of the following sets. The negative rationals, non-positive rational, negative rationals. So at negative rational points, the derivative does not exist. The positive integers except one, and the reciprocals of positive integers. So every negative rational, and then the points one, except one, 2, 3, 4, 5, and then 1/2, 1/3, 1/4, 1/5. These are precisely the only points at which the function Cp fails to be differentiable as a function of x. Now, that's not an easy theorem because you have to go down into understanding basically how to pass the derivative outside an expectation to inside an expectation somehow. And there is a lot of sort of things that have the combinatorial / number theory results that one has to use here. Okay, so I don't have the time to go to the details. There is a paper that we wrote a few months ago at the beginning of the COVID. COVID gave me the opportunity to sit down and finish the paper. And then let's do the following thing. The infinite bin model was associated to the Barak Erdos graph. The infinite bin model, besides giving the results that I told you in the beginning, also gives us ways to simulate the graph and in fact do a so-called perfect simulation to obtain quantities that are related to the stationary distribution of this infinite bin model, which means that theoretically you can put things on the computer and sample directly from the stationary distribution, and one product of this simulation would be precisely the constant C of P. Since now we know nothing about Cp of x, except when x is minus infinity, and we know something now described by this theorem about the behavior as a function of x, we said, okay, let's find out the corresponding infinite bin model if there is anything, and let's see how we can do perfect simulation rather than MCMC in order to obtain quantities related to the stationary distribution. Now I'm going to describe you the corresponding infinite bin model, which we call auxiliary particle system. I don't know, not a very good word for whatever. So for the Barak-Erdos graph, we have the infinite bin model. For GP of x, we have the auxiliary particle system. The auxiliary particle system, to describe it properly, you have to think of it as a Markov process in the set of point measures on R. I use the terminology point measure instead of point process for a measure that is integer valued and when it is not necessarily random. So this is a nice metric space, and I have I want to define two operations in order to describe the evolution of the auxiliary particle system. The first operation is at the point. So if I let nu be a point measure, so just points, a countable set with no accumulation points, then at the point at A, nu plus delta A, and then shift sigma by B means sigma B of nu is nu of a set minus B, which means put the origin at B. Okay, so here is a function that describes the evolution. Take nu, add the point at A, and shift by the positive part of A, which means the following. If A happens to be negative, do nothing, just add the point and be happy. If the point is positive, if A is positive, then shift by A and put the origin at A. So this way, you always have a a point measure supported on the negative real line. Okay, so whenever you put a point, you shift to that point. This is like saying I have this bin system that I told you, and I always insist in labeling the rightmost bin by 0. Okay, so this is a function f(a). It's very well defined function. Trying to iterate this function a few times give you something complicated. So how do I introduce randomness? Well, I introduce randomness according to a geometric random variable. So here it is. I let the alphas be IID Bernoulli random variables, 1 with probability p, and then I look at the first index that we have 1, the first index that we have 0. Obviously, these indices are one of them must be 0. The other one is whatever it is. Okay, so I put color blue here because it corresponds to connecting by a blue edge, and red because it corresponds to connecting by a red edge. All right, so then what I do is I define a C1 plus 1. So look at the first blue point, add 1. Look at the first red point and add an x. And then take a maximum with respect to the leftmost point that you have. And this describes my parameter a here. So it's f at this point of nu n minus 1 that will describe precisely what this auxiliary process. So if one follows these definitions, then you have that this is the Markov process that I'm interested in. Now, how is this related to the actual graph? Here it is. How do we obtain the auxiliary particle system from the weighted graph? Well, we let Vx0n be the maximum weight of all paths on the chunk 0n that ends at n. I know that points will be connected eventually, so I don't care if to take a maximum over all paths between 0 and n, or from somewhere and ending at n. So for some technical reasons, we want to do that. And let mn be the maximum of 0 and so on vn. It's okay? So what I am going to do is I'm going to take each vi and put a delta mass at each of these vi's, and then shift by mn. That is what I call mu n. Well, it turns out that mu n is something that satisfies a recursion like I gave before, and therefore it is the auxiliary particle system. And since I have the auxiliary particle system is a Markov process, I can have now lots of things from the analysis of the Markov process. In particular, I have that this quantity that I described before converges to Cp of x. So I can obtain Cp of x by an MCMC method. The last slide says that I can actually obtain it by perfect simulation. And that requires quite a bit of work, which I will omit now. So this means that Cp of x cannot just be obtained by a Cesaro average, but also by somehow putting this Markov chain in steady state by doing an appropriate coupling, create a stationary process y tilde, and then taking its expectation. I can do its expectation by generating samples from this stationary process, and then taking averages from the random variables y tilde will have the stationary distribution. So I can obtain Cp of x by sampling from the correct distribution. Okay, now, many interesting questions one can ask. This, I promise, this is my last slide. I said in the light traffic regime, in the Poissonian limit, we get the Puit, and we can obtain many differential equations. We have not looked at how one can solve them. We know existing results, some, for example, some very rough analysis by the physicists, in particular Ito and Krapivsky. They are at Boston University, where they look at this equation and say, but these always have a traveling wave solution. And this traveling wave solution has been described in other papers, more rigorous papers. Then there is the problem that I told you about the trace window distribution being obtained by a single limit. We obtain it by a sliding flat window. Can we get rid of this restriction? That's a hard problem. The connection to random matrices is indirect rather than direct. How do we obtain that directly? There is no reason for having the model in 2 dimensions. We would have in 3-dimensional lattice and so on. But another interesting sub-problem is, if we look at the Brownian passage percolation problem here, and there is a maximum, there is certainly a point at which this maximum is achieved. So if we call this point ST, it's a function of the window T, what is the law of ST? Right. That's an interesting question that we haven't been able to solve. Of course, I would say, again, taking my applied hat, but also mathematically, to make meaningful questions, look at the applications, because there are, a billion questions to ask. And I can't say I understand all the statistical physics behind in order to ask these meaningful questions. And the last question is, what can we say about CP of X jointly in PX? That's another hard problem. Okay, so I won't tire you more. I will finish here.
Thank you, Takis, for an interesting talk. So does anyone have any questions? If you have a question, just unmute yourself and ask away.
Can I ask one, Nathan?
Yeah, please go ahead.
Yeah. I was wondering on question 5, do you have any empirical description of the law of ST? Do you have any pictures?
No. In fact, this is a question that Svante Jansson asked me, but I didn't do much about that. So I heard an interesting idea about trying to relate that to heating times. I worked on it for about an hour. I didn't get anything. So no, I don't know anything. There is a kind of symmetry there, as you see. There are some things that you can say, but nothing explicit.
Can I ask, when you're proving this graph converges to this PWIT in this, you said it converges weakly, so that's like with respect to this like Gromov-Hausdorff topology or something?
No, with respect to the topology that is basically the local.
Weak local.
Yeah.
Ah, okay.
Yeah.
So you look at proof by some direct coupling, or
Oh, actually, yes. It is boring. Rather, I mean, when I looked at that, no. Let me be. The result is obvious. The proof to do that carefully is not so obvious. One has to write down some things. So we wrote a paper last year in the Journal of Statistical Physics, but it wasn't that well received, I think, by the reviewers, because they thought that we're proving the obvious. But it is not obvious, I mean, one has to prove something to be able to, with full conscience, say, yes, I can now take continuous functions and say that the distribution converges to the corresponding distribution of the functional for the PWIT, that kind of thing. So now I can say, yes, it is true. But this, with respect to this local topology, there is this survey paper by Aldous and Steele that describes this.
Right. So you choose a vertex at random and look at its neighborhood.
That's exactly right. We choose the vertex 0. So the thing is to prove convergence of the connected component corresponding to 0. That converges the PWIT. Okay. So that means that the graph opens up there, and there's no in the original graph. Of course, there is a possibility for 2 directed edges to go and end up at the same point. But when P becomes small, that vanishes and you get a tree.
Yeah.
It's not an almost sure result. It's, well, I guess if we take some kind of embedding theorem, then it's almost sure in some probability space.
Sure. Okay, other questions?
Excuse me, I have a question.
Yes. Please.
Consider the minimal path between 0 and n. And
Yes.
as you said, it has
The-
length proportion.
Sorry, did you say the minimal or did you say minimal?
Minimal, the smallest path. Yes.
Ah, that's a different question because we consider longest paths.
Oh, you consider longest path.
Yeah, everything is longest path, yeah.
Okay, consider the longest path between 0 and n, and
Yeah.
the length is proportional to n, as you do.
Yes.
So,
Yes.
is it true that the first vertex of this path, the distribution of it is tight?
Is
And
what?
if so, the distribution of the first vertex of this path, other than 0. And if so, is it true that the path converges in distribution to an infinite path?
There could be two paths that achieve the same ln. And the first question is to show that there is a unique path asymptotically. I'm not sure about that. I'm really not sure if it is unique because of the prevalence of the skeleton points. No, I don't know. So if it's not unique, I mean, there's a random number of paths that achieve this ln, and just out of my head now, I would say yes, there are. We choose which path, and I don't know the answer to this. Yeah. But if I'm to make one remark to what Andrew asked about this ST, the question is interesting because and it is related to your question. The question you just asked, it will be ST will be asymptotically the point at which the longest path leaves the lower line and goes to the upper line. So that has some interest in describing the structure of the path itself. But that's the point of a transition rather than the first point or the last point.
Okay, thank you.
All right. Maybe we should wrap it up just looking at the time. But thank you, Takis, for a nice talk and for getting up early to do this. Yeah.
Thank you. I mean, thank you for shifting.